Already talked about moment generating functions for discrete random variables, and as before then, moment generating functions, whatever those things are, moment generating functions, m sub x of t, they will say that they exist, or the moment generating function m sub x of t exists if it is finite on some open interval I, such that 0 is an element of I, some open interval around 0. And the moment generating function for a random variable is defined to be the expected value of e to the tx. Now, remember we said that it turns out that moment generating functions don't always exist. It's just a little problem for some random variables, but most, if not all, the ones we consider in this course will in fact have moment generating functions that are finite on some open interval that contains the origin. So we won't have to worry about that stipulation much. And in the discrete case, like we already saw, this is the sum of e to the tx times the chance that x takes on the value of little x. Okay. Or in the continuous case, I know how to write this out now. It's the integral of e to the tx times the density of x dx. Okay. So this is how we can get moment generating functions for continuous variables like gammas and exponentials and etc. Uniforms. This is wrong. It's supposed to be discrete. Gosh, I need to go back to high school. Okay. As before, we had this nice result, right? It says that if I want to get the kth moment, or also remember this is the kth moment about 0. It tells you something about how x sort of varies on average about 0. There's this nice result that says that this is the kth derivative of the moment generating function of x with respect to t as t goes to 0. Okay, this is why this is why we call these things moment generating functions, because they generate the moments. You can differentiate the moment generating functions and take it as t goes to 0, and you get the moments. Okay. So also something else that might pop out, pipe up, pop, pipe out or up. Something that might be important to us is to take a look at functions of random variables. So what about the moment generating function for a function of x? Okay, maybe x is the number of gallons of water that you use in a month, and maybe g is some kind of a cost function. Okay, and so maybe you're not actually necessarily interested in the volume of water that you use, but you want to know how much the random cost is going to be. Well, the moment generating function for g of x we can write as, well, guess what? It's the expected value of e to the t, and then you put your random stuff here. G of x is now my random variable, really. It's the random quantity that I'm interested in. And so if x is a discrete variable, this is just the sum over all x values of e to the t g of x times the probability that x equals x. Or if x is a continuous variable, it's just going to be integral over the reals of e to the t g of x times weighted against the density function for x dx. Okay, if continuous, if discrete. Okay. Now let's find the moment generating function for a gamma random variable. Gamma random variable. Find the moment generating function for x distributed gamma, alpha, beta, alpha, beta, disco, gamma. Alright, how do you do this? First of all, I know what the answer is. I can look it up in the back of the book, right? I can look it up in the back of the book in that table. But let's see if we can derive it and get it right here. So x has the gamma distribution with parameters alpha and beta. I know, first of all, how to write this thing down since gammas are continuous. It's the integral over the reals of e to the tx times the density function, right? This is just the definition. This is just the definition for moment generating functions for the moment generating function for a continuous random variable. The next step is to substitute in the density function for a gamma, which for a gamma alpha beta, it's x to the alpha minus 1 e to the x over beta all over beta to the alpha times gamma of alpha times the indicator function of x being at least 0. Remember that part? Okay. Now, maybe at this point, maybe this would be a good time for you to pause the video and see if you can finish this off and get it whittled down to the expression that's in the back of the book. I am going to keep on keeping on. Okay, so what does this turn out to be? Well, let's see. I'll tell you what. I'm going to do two things in this first step. First of all, I'm going to pull out that beta to the alpha gamma of alpha stuff. Remember, we did this before when we fiddled around with the gamma distribution. Also, I'm going to get rid of that indicator function in the integrand, and it just tells me that integral is, or that integrand is 0 when on the negative half line. So I'm just going to be left with this kind of thing, I think. So e to the negative x over beta dx, right? Okay. Now I see some e stuff here. I'm going to bring it together and add the exponents. 1 over beta to the alpha, gamma of alpha, times the integral 0 to infinity, x to the alpha minus 1, e to the, can we do it like this? Negative x times 1 over beta minus t dx. I can do it like that, I think. Right? Okay. Now at this point, I'm going to set star. I'm going to define a new variable called star, and I'm going to set that equal to 1 over beta minus t. Okay. The reason I'm going to do that is because, like a good little math person here, I'm looking at this integral and I think, man, that looks familiar. It looks awfully familiar. It looks a lot. This integrand looks a lot like the density for a gamma, right? So if I can put some beta gamma stuff down here in the bottom and then set this stuff equal to something, then this will actually look just like the density function for a gamma. So I'm going to set star equal to this stuff. That way, take a look. See? This is genius. Genius. You always wondered what genius looked like. Well, you're looking at it. I stole this right out of the book. It's not genius. Alright? dx. See that? Dividing by the star there. Dividing by star. Now, to make this look like a gamma density, I think maybe what I'm going to do here is multiply and divide by something, right? What do I need to do in here to make it look like a density function for a gamma? divide by that stuff, but then I've got to multiply by that same stuff in order to keep the equals, to keep it equivalent to what was before, right? So I'll put a star to the alpha times gamma of alpha out here, okay? Perfect. Now I know that all of this stuff evaluates to uno. Isn't that fantastic? And so I just get star to the alpha times gamma of alpha over beta to the alpha times gamma of alpha. Of course, those cancel. And what is star? Star was equal to 1 over beta minus t, all under 1, right? Oh, uh-oh. I better get out my red pen there and draw a line there. Alpha. All right. And I've got beta to the alpha down here. Okay. So this all, I guess, this all looks like this is a bunch of stuff raised to the alpha, isn't it? A bunch of stuff raised to the alpha. It's actually 1 over beta minus t beta, or 1 over 1 minus t beta raised to the alpha, or 1 minus t beta raised to the negative alpha. And that's it. That's the moment generating function there.